Hello, everyone. Hope all of you are fine. Today, we are going to discuss scattering theory and Born approximation approach. Scattering theory is very important in that the Born approximation is again a very important part. Scattering theory, where many approximations are given. One of the approximation is given by Max Born, a German physicist. First, we try to see that what is the approximation. Let me share three different stories regarding the approximation. When I was studying in a college, we used to subscribe very famous magazine, Reader's Digest. At that time, I read one article in one of the issues of Reader's Digest. And article was on very famous fruit, durian. Durian is not available in India, but it is widely grown in Far East region, means Singapore, Malaysia, Thailand. And it is a national fruit of Singapore. In that article, the picture of durian, probable taste, and different type of delicacies made out of durian was given. I was fascinated to taste durian. I had an imagination that how durian would taste, but till I taste it, it would be just imagination. And 5 years back, I had an opportunity to visit Singapore to attend one international conference. And there I took an opportunity to taste durian. So at least after 30 years, I came to reality to taste durian. Till then, it was a just imagination or approximation regarding the taste of durian. When we were studying in a college, at that time, pizza parlors were not there. Only in metropolitan cities like Mumbai, the pizza parlors were available. So one of our friends visited Mumbai and tasted pizza. And he was describing about the taste of pizza. And we had imagination that I take a thick roti, then apply a tomato paste, then sprinkle onion and bake it. It becomes a pizza. But it was nearer to pizza, but it was not a real pizza. So real pizza means if you go to a particular pizza parlor and taste pizza, then it is a real taste. Otherwise, it is a just imagination or the approximation. Now I come to the third part. Then we have seen Kashmir in many movies and many photographs. Beautiful mountains, snow-capped mountains, green forest, and flowing rivers. That's very beautiful. And we want to visit Kashmir, then we'll have a real experience. But if we are not able to visit Kashmir and we'll try to visit nearby hill station, we'll get a feeling like Kashmir, but it is not a real Kashmir. And that is again an approximation. Now, approximation is nearer to reality, but it is not exactly reality. Now, in these three incidences, we can have a reality or real experience by tasting durian, by tasting pizza, or visiting Kashmir. It is physically possible. But in case of atom, it is not possible. We don't have any spaceship on which we can ride and we can visit atom. There we have to just do the approximation. And that approximation is nearer to reality, but it is not 100% reality. And every time we have a one approximation, then we have another approximation, and those approximations are modified by different type of mathematical approach by different researchers. And those approximations are nearer to reality. And reality means the experimental results are explained by these approximations. So today we are coming to the first slide regarding the Born approximation. In this Born approximation, the Max Born gave uh, this particular approximation. Born approximation, German physicist Max Born in 1926 gave this approximation. The approximation says, suppose the deviation gx of ux from the free particle wave function e to the power ikz is relatively very small. Then we have a modulus gx because gx can be positive or negative. So we have taken a modulus gx. It is equal to modulus ux minus e to the power ikz, and that is very, very much, very, very less than modulus e to the power ikz equal to 1. And e to the power ikz is the free particle wave function. So difference is very small. That is the Born approximation. It looks to be a very simple mathematical approximation, but it gives a wonderful result. Now replacing unknown ux to a good approximation by e to the power ikz equal to e to the power ik0 dot x. It's a vector product, where k0 is the wave vector of magnitude k in the incident direction. So the resulting expression is called the first Born approximation to f theta. Now, using equation number 1, where f b theta phi is equal to minus 1 upon 4 pi integral e to the power I k dot x ux small ux d2. Now putting the value of ux, so fb theta phi equal to minus 1 upon 4 pi integral e to the power minus I k dot x u x e to the power I k dot x d2. And those are exponential terms. So just we are combining it. Fb theta phi equal to minus 1 upon 4 pi integral e to the power minus I k minus k0 dot x ux d2. Now we are taking a resultant vector capital K is equal to k minus k0. So putting this into the last equation, we have fb theta phi b for Born equal to minus 1 upon 4 pi e to the power minus I k dot x, it is capital K, ux d2. So we call it as equation number 2. Now we come to the next slide. The scattering cross section is defined. We have already defined earlier that d sigma by d omega is equal to modulus f theta phi square. Now differential scattering cross section is d sigma by d omega, d stands for Born, is equal to modulus f theta phi square is equal to 4 pi raised to minus 2 modulus integral e to the power minus I k dot x ux d2 whole raised to square, because we have to make the earlier equation into a square form. Now here h cut k, capital K, is the momentum transferred to the particle in its encounter with the potential. Since the magnitudes of vectors k0 and k are the same, that can be shown by equilateral triangle. So we have shown over here on the right-hand side, equilateral triangle. Now all the three sides are equal. So one is shown by vector k0, another is shown by vector k. And the difference between the two is shown by another vector, this is capital K. So capital K is equal to magnitude of capital K, and that is by trigonometric approach, we can write 2k sine theta by 2. So it is 2k sine theta by 2, and that we call it as equation number 4. Now, we come to the very important part, the scattering amplitude given in equation 2 in Born approximation considered as a function of k, it is capital K, is the Fourier transform of the potential. So it is an exponential part, it is a Fourier transform of potential. In a spatial case, considering spherically symmetric potential. So whenever we take a spherically symmetric potential, we are taking r theta phi coordinate system. And in that case, the vector k dot x, capital K dot x, can be represented as kr cos theta. Now, let me come to the next slide. Now, we are using the Born approximation formulation for r theta phi coordinate system. So that is nothing but our earlier equation that we have shown over here. That is equation number 2, but that is written in terms of r theta phi coordinate system. So fb theta phi or FB theta is equal to minus 1 upon 4 pi integral 0 to 2 pi integral 0 to pi integral 0 to infinity r square dr sine theta d theta d phi ur e to the power I k r cos theta. Now we try to modify. This looks to be a very big integral, but we can modify it very easily. Now taking over here in this equation, we are taking over here cos theta is equal to x. Then naturally dx is equal to minus sine theta d theta. And naturally putting the value of cos theta, the limit is 0 to 2 pi. So 0 to pi. So limit becomes integral plus 1 to minus 1. So limit of the integral becomes plus 1 to minus 1. And taking the limit for phi, full limit 2 pi. So that equation is converted into the equation shown over here. It is minus 1 upon 4 pi minus 2 pi, that is the full limit of phi, and minus sign is due to the minus sine theta d theta. So it is minus sine theta d theta is converted into dx. So it is minus 2 pi integral 0 to pi ur r square dr, and putting the limit plus 1 to minus 1 integral e to the power I k r x dx, because I k r cos theta is represented as I k r x, and sine theta d theta is represented as dx. Then it is minus minus cancels out. 1 upon 4 pi again cancels out with the 2 pi. It becomes 1 upon 2, and integral 0 to infinity ur r square dr. Then just integrating the second integral. So it is e to the power minus I k r x divided by minus I k r, and limit is plus 1 to minus 1. Then further simplifying, it is fb theta equal to 1 half 0 to infinity ur r square dr. Now we multiply and divide by 2. That is shown over here, that we multiply and divide by 2. So we are multiplying and divide by 2. So it is e to the power ikr minus e to the power minus ikr divided by 2 ikr, and it is plus 1 to minus 1. And that is nothing but equal to e to the power ix minus e to the power minus ix divided by 2i, and that is nothing but equal to sine x. So that is represented over here in the last equation, fb theta equal to 1 half 0 to infinity ur r, because 1 r is cancelled out with the r square. Then dr 2, it is sine kr divided by minus k. And this 2 and 1 upon 2 is cancelled out. So it is equal to 1 upon minus k 0 to infinity ur r sine kr dr. And that is named as equation number 6. So it is the simplified form for fd theta. It is an important feature of the Born approximation formula of equation 2 that depends on the momentum transfer only and not on the initial momentum and angle of scattering separately. So in the Born approximation formula of equation 2, that depends on momentum transfer. Momentum transfer is represented as capital K because it is K minus K0. One is the incident momentum, another is scattered momentum. Difference between the momentum is shown by capital K. So it is a momentum transfer. Now we come to another important aspect where the Born approximation is used. It is a screened Coulomb potential. So here the application of Born approximation to Yukawa potential or screen Coulomb potential is discussed. What is the screen Coulomb potential? We have shown here the two diagrams. In one diagram, beautiful fruits of cherry is shown, and a beautiful red cherry is cut, and seed is there. Seed is surrounded by a sweet pulp. And second is the nucleus. It is surrounded by electron cloud. So electron cloud is surrounding the nucleus. So it is looking like a cherry, where the seed is something like a nucleus and sweet pulp is something like an electron cloud. So screen Coulomb potential can be represented by a fruit. Here, the application of Born approximation to Yukawa potential or a screen Coulomb potential is discussed. When electron is incident on a neutral atom, it finds the nuclear charge is screened or shielded by the surrounding atomic electrons. The potential energy varies from minus Ze squared divided by R, that is very near to nucleus, where there is no screening because it is just on the nucleus, to practically zero outside the atom. When you go to the outside atom, there is potential energy approximately equal to zero. Such screen Coulomb potential is given by the following function. And this is also known as a Yukawa potential. So Yukawa potential is shown by equation number 7. So VR is a potential equal to minus Ze squared divided by R e to the power minus chi R. Here, 1 upon chi has the dimension of length, and it is considered as a measure of the radius of an atom. So one can find out the dimension of an atom by using chi. And here, the 1 upon chi has a dimension of length. So it is an indirect measure of the radius of an atom. The Born approximation, amplitude FB theta, in this case is obtained by using equation 7 in equation number 1 and equation 6. All the three equations we have earlier discussed, we are going to use it over. So it is FB theta minus 2mze squared divided by 4 pi h cut square. 0 to infinity integral e to the power minus I capital K dot x e to the power minus chi r divided by r dr. So we have just put the Yukawa potential in this particular formula. That particular formulation we have already derived in equation number 1. So we have used equation 7, equation 1, and equation 6. And just multiplying by 2 and writing that u is equal to 2mv divided by h cut square, and also using the value of equation 7. So we have done modification in this equation just by multiplying and dividing by 2, and also writing for u is equal to 2mv divided by h cut square, and putting the value of Yukawa potential. And using all the three equations, we can write in form of equation number 8. Now, using equation number 6, we can write FB theta equal to 2mze square divided by k h cut square integral 0 to infinity r sine kr e to the power minus chi r divided by r dr. And by using a very standard formulation over here, this is the standard formulation. It is 0 to infinity e to the power minus alpha x cos r x dx is equal to alpha divided by alpha square plus r square. And sinusoidal function and cosine functions are having a complementary thing, so we can use it in our standard integral. And we can using this standard result, we can write it 2z 2mz e square divided by k h cut square 0 to infinity sine kr e to the power minus chi r dr, because one r is cancelled out with r in the integral. So this r and this r cancels out. Then we are applying this standard mathematical formula, and we can write it is something like fb theta 2mze square k divided by k h cut square in bracket k square plus chi square, just using standard mathematical formula. And just by simplifying, we can write it one capital K, and the denominator capital K cancels out this capital K, and this capital K cancels. So it is 2mze square divided by h cut square capital K square plus chi square. Now, using equation number 4 for capital K, and we know that it is 2k sine theta by 2. So FB theta is equal to 2m ZE square, 2m ZE square divided by 4 k square h cut square sine square theta by 2 plus h cut square chi square. Just opening the bracket. And we know that P is equal to h cut k. So therefore, 4 h cut square k square is nothing but 4p square. So therefore, it is modified as 2mze square divided by 4p square sine square theta by 2 and plus h cut square chi square. And we call it as equation number 10. Now it is finite for all angles, and hence the total cross section is given by this particular relation. So integral modulus FB theta square d omega. Now we come to the part of the Yukawa potential. What is its property? So it is given in the last paragraph. If chi tends to 0, in this equation 10, if chi tends to 0, then the potential VR in equation number 7 of Yukawa potential becomes pure Coulomb potential. So let us go back to the Yukawa potential. If chi tends to 0, it is nothing but e to the power 0. E to the power 0 is 1. So it is a purely Coulomb potential. It is minus Z E square divided by R. So it is a purely Coulomb potential. Because the exponential term value becomes unity or 1. And FB theta diverges heavily as theta tends to 0. If theta tends to 0, then the denominator becomes large and numerator becomes very small. So it diverges. This is very small. So numerator becomes very large. So it diverges very heavily. And this behavior is due to the long range nature of the Coulomb potential. So in that case, if theta tends to 0, this term is approximately equal to 0. And therefore, this term becomes very large and it is diverging heavily. And the difference between the two potentials, it is represented over here in the diagram. The red part shows the Coulomb potential and dotted blue part shows the Yukawa potential. So there is a difference between the two potentials. Let me come to the next slide. Because of its slow variation over an infinite range, the Fourier component with k tends to 0 have dominance in its Fourier transform, which is proportional to the Born approximation amplitude. The cross section for chi equal to 0. If you put chi equal to 0, then it is d sigma by d omega Coulomb, because we know that whenever chi is equal to 0, it becomes a Coulomb potential. It's not Yukawa potential. So Fp theta modulus square at chi equal to 0 is equal to me square z divided by 2p square sine square theta by 2 raised to 2. And if you just open the bracket, it is m square e to the power 4 z square divided by 4p raised to 4 sine raised to 4 theta by 2. This is known as equation number 11. And equation number 11 is nothing but this is coincide with the exact classical Rutherford formulation for the Coulomb potential. So we have obtained the classical formulation of Rutherford for Coulomb scattering just by modifying the Yukawa potential. If you take chi equal to 0, then Yukawa potential turns into the Coulomb scattering or Coulomb potential scattering, and that is exactly the Rutherford scattering formulation. So that is represented by equation number 11. Now we come to the last part of today's discussion, that is the Born series. By taking ux to be e to the power ikz in equation number 1, the approximation is said to be the first Born approximation to the scattering amplitude. So if you are taking ux to be e to the power ikz in equation number 1, that is known as a first Born approximation. One can solve the integral by obtaining as a solution of Schrodinger equation using Green's function for ux as an infinite series. So we have already discussed in our earlier lecture about the Green's function. So we have we are using here the primed or dummy variables, and the first integral is shown here that ux is equal to u0x, and it is plus integral g plus x prime ux prime small ux prime d to capital Ux prime is a potential function. And here we have used the flux g Green's function. And that we have already discussed in our Green's function lecture. So this is for the first. Now we are going to use it. One can substitute for ux prime within the integral by replacing x by x prime. And the integration is taken for the variables where x is replaced by x double prime. So the first integral now becomes a complicated integral, and that is shown over here, that ux equal to u0x integral gx x prime ux prime small u0 x prime d to prime. Then we have a second equation, double integral. It is g plus x prime ux prime, then gx prime x double prime, because we have replaced x by x prime and x prime by x double prime. Then it is a u0 x double prime d2 prime d2 double prime, because here is a printing mistake. It should be considered as u0 x prime instead of ux double prime. Then one can substitute from equation number 2 and for equation u double x prime and repeat the process and get infinite series. So wherever it was a u double prime, then you can replace by u double ux triple, and we can go for a long series. So we just write that equation, just replacing equation number 13 into a big equation, that ux is equal to u0x. The first integral is as it is, g plus x prime ux prime u0 x prime d2 prime. Second equation is equation number 13. So it is g plus x prime ux prime g plus x double prime u0. Again, we have made a correction, u0 x double prime. Then third integral, the triple integral, it is g plus x prime ux prime g plus x prime x double prime u x double prime. Then third one is g plus u x double prime x triple prime u triple prime d to prime d to double prime and d to prime. But here, due to the lack of space, we have to introduce after ux, we have to put here that u0 triple. Here also u0 triple x, here also u0 x prime, here u0 x double prime, and here we have to write u0 x triple. Here we have written u0 x double prime. Here we have to write u0 x prime. Here u0 x double prime. And here we have to introduce, we have to put here u0 x triple prime. The expression is a perturbation expansion of ux with the potential V is treated as a perturbation. And the n plus 1th term in this series is the nth order in the perturbation, because n factor of u equal to 2m v divided by h cut square appears in it. Thus, the first Born approximation, where the first u0x is equal to e to the power ikz alone is used for ux, is really the lowest order perturbation calculation. So here it looks to be a complicated formulation, but by replacing the properly x by x prime, further x prime is replaced by x double prime, and x double prime is further replaced by x triple prime. Similarly, all the other variables are replaced in a proper manner. It looks to be a not very complicated process. Now, one thing is that on increasing the order, equation becomes more and more complicated. So that the expansion is seen very clearly, and this expansion can go to a infinite order. Now, we come to the contributors. Max Born, born in 1882 and died in 1970, very famous German physicist and mathematician. And he was the Nobel Prize winner. And his contribution in quantum mechanics is very well known. The second picture is Hideki Yukawa, born in 1907, died in 1981, Japanese physicist and a Nobel Prize winner. Both of them, they've given a contribution. And this is a wonderful picture. And this is a wonderful sketch done by my friend, Dr. Narendra Chavan, scientist in IPR Gandhinagar. He does a lot of good sketches, though he's a good scientist. And this was done by him when he was a student in Sardar Patel University. This is depicting the hostel room with an open book pages from textbook of quantum mechanics by Matthews and Venkatesh. So this is the open book, and this is the chapter shown about the wave packet, and these are the books lying on the table, and that is the hostel room. So he's a very good artist. He did this sketch when he was studying in Sardar Patel University, staying in the hostel. Dr. Narendra Chavan, we are thankful to him. Nice sketch. And the last slide. Thank you very much. These are the beautiful Garamala trees. Now they are blossoming with brilliant yellow flowers in a large number. So thank you very much for patient hearing. Now I stop sharing my slides. Thank you so much.